If I look at this next one, this is an example of our continuous growth. This is following the model A of t equals a times e to the kt. And so when it asked me how many zombies are there when t equals 0 hours, okay, and again it did specify that t was in hours, I could plug the 0 in and punch it into my calculator, but 0 is like the starting value. That's the initial amount, which is this guy. It's just the 500, okay? It's my a value. All right, so this is kind of about being able to read the question and understand what this model looks like. The next part, it says, what is the growth rate constant of this particular strand of infection? Well, the growth rate constant is the k value, which is this guy right here. It's the 0.12. Again, this is just trying to make sure that you understand how these functions work and what the k value is. All right, now we're going to actually do some calculations here. The next one, it says, what is the population after 3 days? So again, I'm going to plug this in. So the population at time t after 3 days, let's see, 500 times e to the 0.12 t, and t is 3 days, so I'm tempted to plug a 3 in here, but again, t is in hours. So instead of plugging 3 days in there, I have to plug it in an hour, so I have to multiply by 72. Okay, that's what I have to use for time. All right, my growth rate constant is per hour if I add the units up here. See, it's per hour because it said in my original problem that time was in hours. So I have to plug time in hours. All right. Now, again, it's just time to plug this into my calculator. So I'm going to do 500 and then e raised to the power of 0.12 times the 72. And notice I put that exponent in parentheses to make sure my calculator knows to raise e to that entire power. And I hit enter. And it asked me to round to 2 decimal places. So it's going to be 282,664.91. Okay? Forgot to circle my last couple answers. All right? So again, just make sure you're careful when you plug these in. Use parentheses where appropriate. I would put parentheses around that exponent. The next one, it says, when will the population reach 1 million? And again, that's from the initial amount, and we went around to 2 decimal places. All right. So I'm still using the 500 for my initial amount. E to the 0.12. T is what I'm looking for. I want to know how long it'll take for this to equal the 1 million. Okay. So the first thing I have to do is I have to isolate the exponential part of the function by dividing by the 500. And this one, you could leave it as a fraction. This one is going to divide evenly, so I would just go ahead and divide it. Take out 2 zeros, and then that's going to be 2,000. E to the 0.12 t. Should have left myself a little bit of extra space here. There we go. And now to solve this one, the best thing you do is take the logarithm that has the same base as my exponential function, but in this particular case, that's the natural log. Okay, because that's log base e, so what happens is natural log and base e cancel out. So I'm just left with the natural log of 2,000 equals the 0.12 t. So now if I'm trying to solve this, 0.12 t equals the natural log of 2,000, I just have to divide each side by the 0.12. And notice that's just a 0.12 now. It doesn't have a logarithm at all. The only thing that has the logarithm is the natural log of the 2,000. So when I plug it into my calculator, natural log of 2,000. Again, make sure you close that parenthesis divided by the 0.12. I hit enter. And so it tells me that it's 63.34, 2 decimal places. And it's 63.34 what? Well, it's 63.34 hours. Okay? Hours. So make sure you have it labeled correctly. Next one, it says, when will the population double? Again, this is from the initial amount. So I'm doing 500 e to the kt, which is the 0.12 t. Again, I want to know how long. Well, if the initial amount is 500, I want to know when it doubles. I want to know when this thing's going to equal 1,000. So again, I isolate by dividing each side by the 500. This time it equals a 2 over here. I've got e to the 0.12 t. And now again, I take the natural log of each side. So I've got the natural log of 2 equals, here the natural log and e cancel each other out, so I'm just left with the 0.12t. Divide each side by the point, oh here I was doing such a good job using red every time I did something on each side. I keep going with that. Divide by the 0.12 on each side, and I find out that t equals, again it's a job for my calculator, the natural log of 2, close those parentheses, divided by the 0.12. Enter. It looks like 5.78 rounded to 2 decimals. 5.78. And again, that's 5.78 what? 5.78 hours. Okay? Make sure you have the appropriate units. Doesn't mean anything without the units. All right? Last one here. It says there are 4 million zombies. Mr. Jansen can annihilate them with a TI-83 bazooka, again, using my mind-blowing calculations, that has a destruction rate constant of 0.35 per hour. How long will it take to cut the population in half? All right, so I want to round this to 2 decimal places again. This is still my continuous model, but since this is decay, since our values are decreasing, it's a times e to the negative kt now. Okay, that's my decay rate model when it's continuous. Now I just plug in what I know. I know the initial amount was the 4 million. E to the negative k, so it's a negative 0.35. T is the thing I'm looking for, and I want to know when I'm going to cut the population in half, so I want to know when this thing's going to equal 2 million. And now, just like I did before, I isolate the exponential function, so I'm going to divide each side by the 4 million. And when I do that, I end up with a 1/2 over here, or a 0.5. Again, because it's a terminating decimal, you can just leave it that way. Equals e to the negative 0.35t. My negative sign is a little bit far away from that guy. There we go. And now to solve this, I have to take the natural log of each side. So I take that natural log of each side. So over here, I'm left with the natural log of 0.5. Over here, the natural log and e cancel each other out, just like they always do. I'm left with a negative 0.35t. Now again, to solve for my t value, I divide by the negative 0.35. And this becomes just a job for my calculator. So one more time, let's show it to you on the calculator. For old time's sake, Mr. Jansen, natural log of 0.5, close the parentheses, divided by, make sure you use the negative sign here, negative 0.35. And I hit enter. It looks like 1.98. And the question is 1.98 what? Well, this was per hour. My original example, this was per hour for my decay rate, so my time is in hours one last time. All right. Hope this was helpful, and good luck on your test tomorrow.